Dear students, in the morning class we have discussed about this pointing vector. So I have stopped at the pointing vector, and the remaining one topic which I left, which covers mainly two things. First, that is the normal incidence and then oblique incidence. So look at this one. So when a uniform plane wave is traveling from one medium to another medium, that is when the wave is incident on the boundary between two mediums, when the wave is incident, we have to consider two conditions. One is the normal incidence and the other one is the oblique incidence. So whenever wave is incident on the boundary, a part of the wave will be reflected back to the medium 1 and a part of the wave will be transmitted to medium 2. So that we are taking into consideration. So how the incident wave, that is the wave that is incident on the boundary, is going to incident because of the two cases we are going to see. One is the normal incidence and the other one is the oblique incidence. So when the uniform plane wave incidence normal to the boundary between two media, it is called as normal incidence. When the uniform plane wave incidences obliquely to boundary between two media, it is called oblique incidence. It is called as oblique incidence. Now, first one, we will see normal incidence at a plane dielectric boundary. So look at this one. Here we are taking two dielectric mediums, medium 1 and medium 2, with the parameters epsilon 1, mu 1, eta 1 and then sigma 1, and epsilon 2, mu 2, eta 2 and then sigma 2. So a uniform plane wave travels along z direction, incidence at right angles to the boundary. So because of normal incidence, it is right angle to the boundary. Oblique incidence means other than right angle. Now, so here in the figure it is represented EI and HI are the parameters of transmitted wave, and ET and HT are the transmitted wave in medium 2 and the reflected wave HR and ER. So go through the diagram and it is clearly mentioned what is EI, HI, ET, HT and ER and then HR. Now, say the field composes of both the incident wave and then reflected waves. Say for example, what is the total, here we have to take what is the total electric field in medium 1. Medium 1 composes incident wave and then reflected wave. So E1 equal to EI plus ER and E2 equal to ET. Similarly, magnetic field components. Now, so already we know between two dielectric mediums, if we take the boundary conditions, the tangential component of electric field is continuous. Similarly, the tangential component of magnetic field is also continuous. So with that condition, here E tan 1 equal to E tan 2. Otherwise, H tan 1 equal to H tan 2. So from this we can write finally EI plus ER equal to ET and HI plus HR equal to AT. So take the equations are taken as equation 1 and equation 2. Now already we know the relation between electric field and then magnetic field. The magnitude of E and H is given by eta equal to E by H. So eta 1 in medium 1 it is EI by HI, or it is equal to minus ER by HR. Eta 2 equal to minus ET by HT. That is equation 3 and then equation 4. Now here we are doing some small simplification. We will take equation 2. In the place of equation 2, H terms are represented by E terms because we are having a relation between E and H. So after solving that one, we will get fifth equation. Now, so add equation 1 and equation 5. So by adding these, ER terms will get cancelled. 2IE equal to 1 plus eta 1 by eta 2 into ET. So this is nothing but from this what you are going to take the ratio of ET by EI. The ratio of ET by EI. So which is equal to here tau equal to ET by EI equal to 2 eta 2 by eta 1 plus eta 2. Is it clear? So this is the transmission coefficient. Remember, transmission coefficient is important. Next we are going to see the reflection coefficient. Now, so in order to get the here transmission coefficient is nothing but the ratio of ET by EI. So now the reflection coefficient is nothing but the ratio of ER by EI. Now, so what you are doing in order to eliminate EI, equation 1 and 5. Now look at equation 5. Equation 5, what you are having? EI minus ER equal to eta 1 by eta 2 into ET. So from equation 1, what is ET? ET is nothing but EI plus ER. So substitute ET from equation 1 in equation 5 and simplify ER by EI, which is equal to eta 2 minus eta 1 by eta 2 plus eta 1, which is nothing but called as reflection coefficient. So tau represents the transmission coefficient, which is nothing but ratio of ET by EI, and reflection coefficient is given by ER by EI. So note 1 plus this rho is equal to tau. So this is nothing but transmission coefficient and reflection coefficient in a dielectric medium. Now, so here some problem is given. Go through that problem. What is this? Is simple problem. E and H are transferring gases normally incident on a surface with a dielectric medium. So with eta 1 is a free space, medium dielectric, eta 1 equal to eta 2. So asked to calculate transmission coefficient and then reflection coefficient. So if it is free space, eta equal to 125. If it is not free space, eta equal to root of mu naught mu r by mu naught epsilon naught epsilon r. If it is a free space, it is nothing but root of mu naught by epsilon naught. Otherwise, if it is a medium, it is root of mu naught mu r by epsilon naught epsilon r. Now, so already we have completed normal incidence. Already we have completed normal incidence at a plane conducting boundary. Now what we are taking? Now we are taking normal incidence at a plane conducting boundary. So one is the dielectric medium and the other one is the conducting medium. So in this case, as we know, in a conductor no wave will be transmitted. It indicates no wave will be transmitted and the entire wave is reflected back to medium 1. So these waves superimpose and forms a standing wave. Look at the figure. The wave is incident and completely the wave is reflected. There is no transmitted wave into the conducting medium. So because of this, a standing wave will be formed because of incident wave and then reflected wave. Standing wave means which is a standstill wave which cannot be propagated. So that standing wave is represented as EIS. EIS equal to EI plus ER. EI is taken as EI e power minus gamma 1 z and ER equal to e power minus gamma 1 z. Both are propagating in opposite direction. So both are represented here. So already we know in a lossless medium alpha equal to 0. So gamma equal to j beta. Simply gamma is replaced by beta. So EI e power minus j beta z plus ER e power j beta z AX cap. Now ER equal to is nothing but minus EI. So EI e power minus j beta z minus EI e power minus j beta z. Minus EI is to case common, which can be equated to 2j sin beta 1 z. So minus 2j EI sin beta z AX cap. You got this equation. Next, so if it is a time varying field, then what do you have to do? E1 equal to E1s into e power j omega t. So what you got? Minus 2, this you take into consideration into e power j omega t. So e power j omega t can be represented as cos omega t plus j sin omega t. Now by multiplying this one, taking only the real quantity, E equal to 2EI, that is magnitude of EI sin beta z sin omega t AX cap. Similarly, by solving HIS, we will get the same equation where 2HI cos beta z cos omega t AY cap. By taking this, what is this we are having? By taking the components, and remember here HR is equal to HI. HR equal to HI, whereas only this ER equal to minus EI. Because of this, we got a cos term here in this equation. Here we are having HI equal to HR. In this case, in the previous case, we took EI equal to minus ER equal to minus EI. So we got in the sign terms. Finally, H we got in the cos terms. So EI is the one equation and the other one is the HI. So these are the two equations which we got when we are having a normal incidence. Normal incidence when we are having a dielectric and a conducting medium. So here So this is the note which is overall whatever the equations I have covered, whatever the equations we have covered, they kept these equations. So next we have to go for the next thing. As I told, when the wave is incident, we have to take two conditions on a boundary. One is the normal incidence and the other one is the oblique incidence. So normal incidence, again we have to take two cases, that is between two dielectric mediums and one conducting medium and a dielectric medium. So total 4 cases we have to study. In that only we have studied up to 2 cases. What is that? Normal incidence between two dielectrics and